Welcome back to the second part of current sense amplifiers. In the first part, and there should have been already a card and there's a link in the description, we talked about why you might not want to use a general purpose op amp as a current sense amplifiers, and we talked a lot about common mode voltages, a little bit about output swing and rail to rail, and a whole lot about common mode rejection ratio and all the math and log and decibels around it. Sorry for that. Today we will have a look at some current sense amplifiers that are out there. Only 5 from 4 different vendors, don't worry. And finally, because I already told you I have laying it around, we will actually build a current sense amplifier using that LT6105. Yeah, I have the circuit here. Magic of video editing. I made the intro after I finished the video. Well, anyway, let's get started. The first one I have for you here is from Texas Instruments, and it's the INA181. It's a very simple one, and if you look at its functional diagram, you see it's basically exactly our differential op amp, with the exception of the reference output not connected to ground. I mean, you can connect it to ground, but you can set that to a voltage wherever you want, giving you the ability to measure positive and negative currents in respect to your positive and negative input. Yeah, just as a side note. And another side note, Texas Instruments also has a really good parametric search for their current sense amplifiers offerings on their website. And I think for most of the devices, they have a little app where you can input your parameters like common voltage range, your operating voltage, the current range you're measuring, and stuff, and then it calculates you an error curve in respect to the measured current. Very nice. But back to the device. So these INAs 181 come in 4 different variants with 4 different gains: 20, 50, 100, 200, and they have a minimum CMRR of 84 decibels. Now, if you remember, and if I can find it, for 0.1% resistors, the CMRR was 88 decibels with our op amp. And yeah, worst case. And they offer 84 decibels, worst case, minimum. If you think about that, 0.1% tolerance resistor sets you back about 50 cents or so, or maybe only 40 cents, I don't know, if you don't buy them in bulk. The price of 50 cents for the whole package, about-ish, yeah, that's a nice offering. Common mode voltage independently from the supply voltage, so you have not the problem like with an op amp that you have your supply somewhere up here, is minus 0.2 to 26 volts. Okay, all reference to ground. Don't care what your supply voltage is. And yeah, wouldn't work quite for our application. For our example, that was 40 volts, but nevertheless. And the low output swing of the output is maximum, worst case, 5 millivolts over ground. Yeah, you remember in the first part of the video I said rail to rail is really just almost to rail and almost to rail when we're talking about rail to rail outputs. Yeah, and total gain error, again, worst case, plus minus 1%. So it's a really nice piece if you don't have any special requirements. Next on my list is from Maxim, the MAX9918. That's the diagram here below. And this is a variable gain current sense amplifiers. You basically set the gain via two resistors. And they say the gain is from 30 upwards. I haven't read through the whole data sheet, so I cannot really say how far you can turn up the gain. I think 200 or so, might be pushing it, but 30 plus. Common mode rejection ratio is 80 decibels, and that's very interesting. The common mode voltage, measured to ground, don't care about VCC, is minus 20 volts to 80 volts. So, and output low swing, in respect to ground is 10 millivolts maximum, worst case. It's a little bit more expensive, costs you $1.50 about-ish, and but the gain error, total gain error, is only 0.6%, worst case again. So a nice part if you need somehow a specific variable gain. It also has a reference input, so you can shift the 0 volt output in respect to ground up, because it's also able to measure currents in both directions. So you can have positive and negative voltages here at your input. Maxim has also a parametric surge, but it's if I remember right, you have to decide from the beginning first if you want to have a look at precision current sense amplifiers or automotive current sense amplifiers. So they guide you. You have the decision to make the decision up front, while Texas Instruments simply puts everything on one side. And third, we have another Texas Instruments part, the INA28X. The last digit designates the available gains, which are 50, 100, 200, and 1000. And this little bugger has a staggering common mode rejection ratio of 120 decibels. You remember 88 decibels? If you use an op-amp, 0.1% resistors. 108 decibels would be 0.01% tolerance resistors. And these set you back, no longer sense. We are talking whole dollars here. And this thing does 120 dB. So 128 dB, 0.001% resistors. I don't think you can buy those, not normally. And it sets you back only $2.50. Of course, if you look at the block diagram, you notice there is some black magic going on here. Yeah. So there's a first stage, which is, I think, internally switched to the first amplifier, which is not resistor based, but capacitor based. And then comes your usual differential amplifier in a second stage. And I guess this is how they implement this, worst case 120 decibel common mode rejection ratio. V outswing low is quite high, 40 millivolts measured to ground. But you also have the two reference pins outside, and they are so nice to already include a voltage divider here of 33.3 kilo ohms, 2, so 50-50 inside the chip. So if you connect the one reference pin to your supply voltage and the second reference pin to ground, your zero output is exactly halfway between ground and your VCC. Also very nice. Total gain error, to my surprise, quite high, plus minus 1.4%, worst case. But yeah, well, nevertheless. Common mode voltage with that circuit goes also up to 80 volt and goes down to minus 14 volts. Number 4, something from ST Microelectronics. ST Microelectronics does not offer, to my knowledge, parametric search on their website. They also have not that many types, maybe a dozen or 2 dozen, more like a dozen. But they have interesting things. I mean, we have now amplifiers with fixed gain. We had amplifiers with variable gain through external resistors. And that bugger here, you can choose the gain in fixed steps through 2 digital inputs. And the gains you can choose from is 20, 25, 50 and 100. The picture already shows what that's for. So depending on your current range you're currently in at your sense resistor, you can choose the gain accordingly to use the full dynamic range of an analog digital converter in your microcontroller. Yeah, you remember the example from my first part. Yeah, common mode rejection ratio, very vulnerable, 90 decibels. So beyond what you can do with 0.1% resistors. Common mode voltage, yeah, not all current sense amplifiers are equal, is a positive 2.9 volts to 70 volts. So for my application, yeah, here as sensing the current in a lab power supply with the load going down to almost 0, that's without any additional circuitry. You can do that with that chip. There's always a possibility to connect the negative VCC not to ground, but to have really a negative rail in that case. But then we are back at the same drawbacks regarding common mode voltage with a run-of-the-mill op-amp. And but if you have an application where you don't go below 2.9 volts, it's okay. The total error, and this is I took the absolute worst case from the datasheet under, I say, normal conditions. This is order of magnitude lower, but it's not the most precise part. So plus minus 22% in absolute worst case conditions, which is abysmal. So when you use that, you really have to read the datasheet and all parameters given in it. And yeah, it sets you back to 50. Yeah, that one also. Order of magnitude, $250. At that point, I should mention that there are current sense amplifiers out there who don't have an analog output, but the analog to digital converter already integrated. So you get some normally serial output, I squared C or something like that, SPI, to get your values directly in digital format out. I've also seen something that gives you a frequency modulated output. Yeah, the higher the current, the higher the output frequency. I don't know who would use something like that, but I guess it's useful in some application. And at last, we have the LT6105, which I happen to have laying around from Analog Devices / Linear Technology. Please forgive me, I don't know which company bought which or if it was a merger. Yeah, whatever. Yeah, the data sheet says you can set the gain from 1 to 100 via 3 external resistors. Yeah, this is a little bit of a different beast. Also because it has a current output. So basically what you do, these two resistors here determined how much current you get out of the thing in respect to the voltage drop over your sense resistor. And then the output resistor, yeah, the current going through here basically determines your output voltage. One note, if these resistors are a little bit different, it doesn't impede on your common mode rejection ratio, which is also a very good 100 dB, worst case. It influences the amplification in some ways, but not the common mode rejection ratio. Common mode voltage minus 0.3 to 44 volts, which would be ideal for our example here. Output low swing measured to ground is worst case 40 millivolts. And yeah, we'll see why this can really bite you in the behind. Also 250 a piece, yeah, if you buy them not in bulk. And gain error, worst case, plus minus 1%. In our next chapter, not in the next video, just the next chapter here, we build our current sense amplifier. So I already have my shunt resistor now and my current sense amplifier, which has magically grown pins. Yeah. Can I have a focus here? On the breadboard. And if you want to know how I soldered this really small pins onto the adapter board card link, let's go back to the board then. Yeah, And our goal is to, from the 50 milliohms of the sense resistor, we have a maximum current of 400 milliamps through it that will yield us a maximum sense voltage of 20 milliamps. And on the other hand, we have our analog instrument, and that needs for full scale 40 microamps, has an impedance of 5 kilo ohms and is a voltage drop of 200 millivolts. So from 20 millivolts to 200 millivolts, if we would just rely on that initial amplification formula of the data sheet. But we have this worst case low output swing here, which is 40 millivolts worst case max over our negative supply. And 40 millivolts of 200 millivolts maximum. Nah, that's not working. What is that? 20% error? Yeah, something like that. 20% error. So we never would go down, or 20% of the full scale. So worst case, we never would go down to 0, but we would be at 20% of our displayed 400 milliamps, which would be somewhere like 80 milliamps. It would sit there even with no current. Worst case. We will see if the worst case comes to bear. So no, that's certainly not happening. So we have to dig a little bit deeper into the data sheet, and if you do that, I'm not showing you the fine print, just the facts from the data sheet. There is somewhere the mentioning that the voltage amplification of that thing is ideally between 1 to 100. Okay. So, and 200 times 20 millivolts. So if we aim for a voltage amplification of 100, then we have our V out is our voltage amplification times our V sense, and this is 20 millivolts times 100. Sorry, turned it around here. And this gives us 2 volts. Now back to the worst case 40 millivolt output swing, low output swing. So we have now I call it a low swing error. Of only 2%. Worst case. So these are our 40 millivolts of our 2 volt scale. So okay, we better go with a higher amplification to get a higher output voltage on full scale, so we avoid that low swing problem, or minimize that low output swing problem. Almost rail to rail, as I said. That's the one thing. The other thing is, this is not a voltage amplifier. I mean, they give you a formula here for voltage amplification, but it clearly says here, this is a current output device. And that's the next formula, which is from the data sheet, which is important for us. So I out, the output current, is equal to the sense voltage over the input resistance. And luckily, our analog instrument is also, of course, a current-driven device, not a voltage-driven device. I mean, it has a really low impedance. I mean, there will be a voltage drop, but it's basically current-driven. So we need at our output, yeah, I can use that graphic, we need at our output at least 40 microamps. And if we rearrange that formula a little bit, then our Rin, yeah, is equal to V sense divided by I out. That's easy. Our V sense was 20 millivolts. And we want 40 microamps as output. Yeah, and that's 500 ohms for our input resistors. And again, checking with the data sheet, yeah, there you find somewhere that the optimal range for the input resistors is indeed between 100 ohms to 1 kilo ohms. So yeah, we are fine on both ends. Amplification, yeah, we go to the maximum that they want, and input resistor is also in range. The only thing we need now to calculate is our actual output resistance we need to get to our 2 volts, and that's quite simple. I already told you that the data sheet tells you that our amplification is R out over R in. R out over R in. If we want to know our R out, that's simply our amplification times R in. So that's 100 times 500 ohms. And this is 50 kilo ohms. Okay, we finished our circuit. And it would look something like that. So we have our 50 milliohms sense resistor, our 500 ohms input resistors, which will yield us as a maximum sense voltage here of 20 millivolts, a current of 40 microamps, which should go into our instrument, and we need to get up here at the output to 2 volts. Yeah, a total resistance here to ground of 50 kilo ohms. Now, first, I don't have a precision resistors here. Second, this is probably not really, it is a very good analog instrument, but yeah, these are nominal values. So if we want to use a trim pot, for example, to tune the whole thing, at the end of the day, we need a little bit more current out here. And yeah, so let's go here with 430 ohms. Okay, this will produce a larger current here. So our output current, we sense divided by R in, and this is now our 20 millivolts divided by, what did I say, 430 ohms, and this would yield us a current of, yeah, consulted the calculator, it's 46.5 microamps something, but let's say 47 microamps. So we got now here out at full scale 47 microamps. And that means we can have here something like a pot and probably another resistor, and we will have a current here of, yeah, 40 microamps should go here, 7 microamps should go here, so about 7 microamps. Okay, and our total resistance here should be, yeah, we still want to have 2 volts output. So 50k here. So we need 50 minus 5k. A series resistor here with 45k. And here we need something, I need to consult the calculator again, sorry. Yeah, a total of here 286k. Yeah, and probably doesn't do, we don't want to do that all with a pot, so a second series resistor. So yeah, about the values. So I choose 43k here, that puts us down here in total to 48k. So at our 40 microamps we will not quite reach 2 volts, which might increase our error on the low swing of the output towards 0 volt, worst case. And yeah, I simply said, okay, 100k pot and 200k resistor, which, yeah, allows us here to go between 240k and 340k, which should be okay. Please ignore these fine lines. Yeah, this segment of the video comes through the magic of editing back from the future. Sorry about that. So I've built up the circuit. This is basically here the Kelvin connections to our current sense resistor. Yeah, you shouldn't do a 50 milliohm current sense resistor on a breadboard. So I soldered some Kelvin connections here going into our amplifier. And then here on the back, that's simply our 100k pot and our 200k resistor going to ground. And we have also connected to the output our 34K resistor, which then goes to our analog instrument. And yeah, I have connected in parallel a digital instrument too, just to be sure. Yeah, the guy here is measuring the current in milliamps, and yeah, that comes here from the background from my power supply and my not so electronic load, yeah, card link. And now we can play around. I mean, the first thing I've noticed, just yeah, with basically no load, and yeah, we can turn this off to 0 amps. No voltage, absolutely here across our meter. I mean, absolutely nothing. That is our worst case low swing 40 millivolts. I mean, worst case from the data sheet. It doesn't apply here. No problem. There's not a single millivolt. So yeah, we're happy there. Now let's see if we put 100 milliamps. Yeah, it's alive. 100 milliamps, 100 milliamps. Yeah, good enough. And we have here 50 millivolts. Yeah, 200 millivolts full scale. And that's spot on. I swear, swear. No, swear. Whatever. I haven't touched the trimming pot yet. I haven't touched it. Okay? I took it out of the box and put it in. But yeah, we are spot on. And also the analog instrument, I'm looking here at it, is exactly on the 10. So for 100 milliamps. Yeah, that's great. That's great. Let's go the whole mile up to 400 milliamps. And you can already see a faint glow back here, but really faint. $400 milliamps. 199. Yeah. I mean, this is not even a 1% error. This is, yeah, that's really great. Let me zoom in a little really on the scales here. Yeah, I mean, that's perfect. Yeah, trusting that we are here really on 199 millivolts and here almost on 400 milliamps. Okay, now we're a little bit over 400 millivolts here, obviously. Oh, let's switch that back to volts, losing a digit, but I guess that's okay. Yeah, it's spot on without tuning the pot. I'm really surprised. I noticed one oddity. I mean, this is obviously, sorry, already switched that off. Ooh, a little bit too much. 400 milliamps. This obviously works perfectly, but actually, yeah, current in, current out. This is high side, so this, the negative end, goes to my load, and I have an independent power supply. So this little circuit has absolutely no ground connection to the power source. None. And it's working. And I wonder if we, yeah, that goes back to ground, if we give it a ground connection. Yeah, you see there's a slight wiggle. Okay. So, yeah. That's now really the right circuit. And incidentally, sorry, a little bit out of focus. Incidentally, we are now not quite on the mark, so I will have to tweak the pot a little. Yeah, seems to, yeah, I was not completely right with that. 240k resistors, should have chosen one bigger, but I was guesstimating. Near enough. But yeah, it kind of works without a ground connection, which is interesting. And if I look at the power supply, you can't see that, but it's currently at about 9 volts. Now, I'm interested in if I would have allow a very low voltage. Okay, just reduce the resistance here. Ground connection is there. And now I go up to 400 milliamps. Yeah, almost. Yeah, this is now a very low voltage. Not too low. This is 1.4 volts, about-ish. You see we are in the amplification a little bit off now. We are still on 400 milliamps. I will talk about that also. That's a problem with our two 5% input resistors. But if I remove in that mode the ground, yeah, it just wiggles a little bit. It wiggles a little bit. That's all. That's astounding. That's astounding. So we changed our current mode voltage here from 9 volt, something like that, down to 1.4 volts, and nothing happened. Okay, we'll have a look at the datasheet for that stuff. About that slight difference in the output voltage at the same current of 400 milliamps when I decreased the common mode voltage from 9 volts to 1.4 volts. Remember, I'm using here cheap resistors at the input with plus minus 5% tolerance. And the datasheet says if R in 1 and R in 2 are not equal, then we have to use these formulas to calculate the amplification. So in our first case, V minus in was greater than 1.6 volts. The amplification is dependent on R out, yeah, and R in 2. If the voltage, the input voltage is below 1.6 volts, in our case 1.4 volt, the amplification depends on R in 1. So that's how that difference came about when we changed the common mode voltage. How that thing was able to operate as a floating device, so with no connection between the ground of the amplifier and our power ground from the LED power supply, I have no idea. If you know why the datasheet says nothing about it, please, please leave a comment. So, that was basically everything I could tell you about current sense amplifiers, at least from my point of view, how I use them or at what values I look when I choose one, and how where you can choose them. Why not use an op amp? And yeah, don't forget to have a look at part 1. There was a card and a link already at the beginning of the video. And yeah, bye.